I'll do it afterwards. Okay, here we are, 6 minutes after the hour. I have to remember because we'll talk for an hour and do it afterwards. All right, now we're live, I think. Are we?
Uh,
Yes,
I
it
just clicked something to say, is it okay to go live? So, in fact, something says
is.
this meeting is now streaming live on YouTube.
That's right. Here
There's,
we are. Okay, very good. So now I get this out of the way and introduce you. Okay. Hi, I'm Etta Spencer. Today, let's talk about methane, shall we? Methane is at least 26 times worse as a greenhouse gas than CO2. And depends on how you calculate it. Some people say it's like 100 times worse. So it's really bad news to have in the atmosphere nowadays when we want to get rid of some of that greenhouse gas. So if we could get rid of most of the excess methane, we'd be halfway to our goal or something. Some people probably got a real calculation of how much progress we would make, but it would be significant for sure. So can we do it? Is there any way to remove the methane from the atmosphere? Yes, indeed, there is. As far as I can tell, we have some people here who know how to do it, and they're going to talk about it. And we have quite a few today, so it looks like it'll be a lively conversation. I'm not gonna, I don't know what order to put you in, but just whatever top to bottom on my list here. Clive Ellsworth is, I presume, in London, and he has been working with Franz, and I think just considerably also with Peter for many years. And in other parts of his life, he's into software work. And Franz Weste is in Germany, and he is the first person who wrote the first paper on this idea how to remove methane from the atmosphere. And by now they've gone through many iterations, developing various aspects of the proposal. So I'm sure they will bring us up to date. Peter Fikowski is in Silicon Valley, I presume. That's where he hangs out. And he is, by now, he's a habitual attendee here because I call on him every time I need somebody who knows everything about everything. And he's always a good sport and is willing to help me out. So, hi, Peter. Now we have three newcomers, and they're all connected with something called Blue Dot. And Blue Dot presumably refers to the tiny speck of dust in the cosmos called planet Earth, which does have a beautiful blue hue from depends on how you look at it. So Blue Dot, we're going to try to save Blue Dot. And again, I think these people all live around near to Peter in Silicon Valley. Rosia Herbert is something like the outreach director or something for this organization. She has a background in, I think, anthropology. David Hinkle Wallace is the CEO, and he's he's had a 30-year commitment and experience in Silicon Valley as an entrepreneur who's founded and run companies globally on things like solar thermal power, pharmaceuticals, and software. Very good thing to do. And Jeff Schrader is really a newcomer to me. And I was surprised when he popped up because I didn't expect him, but I'm delighted. He is apparently this chief scientist at Blue Dot. So we'll find out more about what he does. So thank you all for appearing. And we will probably be joined later by Adele Buckley, who always comes late, but she's worth having. She's somebody who is a friend of mine. She's very active in the Canadian Pugwash movement or globally in the Pugwash movement, and is an engineer and physicist, retired. And she tends to ask hard questions of people, which I think is a good thing to do. That keeps us all honest. So, welcome, friends. Now, where do we start with this? I'll tell you what. Franz, you are the Papa Daddy of the operation, I think, is your idea in the first place that led to a lot of additional research by others. And can you give me a hint as to what you've been doing lately that no, we should do more basic things. Instead of talking about what's changing, we should tell you people first what it is, what it used to be, what the project was a year or two ago. First time I ran into you folks, you were planning to spray iron salt from a tower on an island in the tropical zone of the world someplace, hoping and expecting that it would change through various chemical steps, change the methane in the air into CO2 and water. CO2 not being something we particularly want, but certainly not, but it's a lot better than methane. So that's what you were going to do before. Now, what have you been up to lately that is that changes that game plan? What is your proposal like nowadays? And Franz, you start that, and I think Clive maybe will be the right one to bring it up to date. Then at some point, we want to talk to the people at Blue Dot about what you're doing and how it connects with what Franz and Clive and Peter, I don't know what your role is anymore in this, but I know you have one. So you're on your own. Just interrupt each other if you need to get us all clear about what you're up to. Franz, why don't you tell us briefly what your current aspirations are?
Meta, you know, the albedo of the planet acts also intensive on the climate temperature.
Mm-hmm.
The more white the planet is, the more clouds it has, the more albedo we have, and the cooler is the surface. And
but that's of course the whole theory behind the marine cloud brightening and SAI, right? But yes. Are you into that too now?
We combine these both things. We know, meanwhile, that clouds also deplete methane, because clouds produce oxidants, OH radicals. And we try to combine now the cloud whitening with an intensive oxidation by clouds. And nature does this, and we only try to optimize this process.
Oh,
you know, the clouds become white when you give them enough cloud condensation nuclei.
Mm-hmm.
If you and above the white ocean, in the tropical regions, you have very
very few. It's these little tiny aerosol particles, isn't it?
You have only 20 to 50 per cubic centimeter of these tiny particles, and they give rather in clouds,
which darker clouds
have darker clouds. Yes.
Mm-hmm.
And what we need to do is only to increase the number of cloud condensation nuclei. The more you take, the more tiny the droplets become, and the more whiter the clouds are, and the longer they exist, because these tiny droplets, they have a surface loading
charge,
a surface charge which is positive, and so they repel each other and cannot coagulate.
And where is it they do that? In every cloud, or do they just in certain areas they would
We
repel
use
each other?
the clouds in the lowest layer. That's cumulus
Yeah.
clouds and
Yeah.
stratocumulus
Now, all
clouds.
of that is straight, you know, right out of marine cloud brightening. There's nothing different about that. How's it connected with the methane thing?
When we make the cloud white, brighter, the droplets become smaller, and their oxidative capacity increase enormous by orders of magnitude.
Yeah. This was only discovered recently, Meta, only in the last few years. The scientists realized that very, very small cloud droplets are, having an effect on methane. Anything, the kinds of things that remove things like methane out of the air and other pollution as well. It's oxidation. It's oxidative radicals. Franz mentioned OH. People thought it was mainly UV and ozone and things in the air that, that's what was doing it. But it turns out there's an awful lot going on in clouds. And the smallest cloud droplets are the most active. And this is what we've locked
now
onto.
Marine cloud brightening then would be active in two ways then? Both in reflecting the incoming sunshine back into outer space and thereby filtering out the light below and the heat below. That's the usual theory. And this now is, you're saying it does extra things at the same time.
That's exactly what we're saying, yes. Yeah.
How come I haven't heard this before?
Well, it's only recently been discovered.
You said the last few years.
The last few years, yeah.
Okay.
Yeah. But pretty prominent people are working on it. Yeah. Jeff's I don't know if it's his tutor or maybe he can speak about it. One of his professors at in California University, I don't know can't remember which one, is working on it. It's Professor Zari and others.
Let me ask Jeff then. Let's go right straight to the horse's mouth. What's the story, Jeff?
Well, wait, I can't speak for Zaire. He's not my professor. He's a professor at Stanford. He's not one of my professors, to be clear.
I thought he was something related to you.
Oh, well, he was personal relationship, not a technical relationship.
We'll accept any kind of relationship as long as you know what you're talking about. That's all I want to hear.
This never know what I'm talking about.
Well, you're way ahead of me because I hadn't even heard of this before. And I don't know why not, because I hang out with these folks quite a bit.
So I
should have been told.
So we're running laboratory experiments based on this now. And we're sort of simultaneously, although not literally simultaneously, running 3 different kinds of experiments in our lab at Blue Dot Change. The ferric chloride, iron salt aerosols, UV, and I now have the materials to run the cloud experiment, which is done through some reactions that I won't go into unless you really care, that were recommended by Franz and Clive.
Well, I'm certainly curious to know, but I also realize if we get into the chemical details, I won't be able to follow you anyway. So let's stick to the level of conversation that I can follow, and therefore some of our viewers can follow. Okay, so
maybe I can suggest, Meta, that we just speak more generally about aerosol interventions. Okay, because whether you're doing this using the clouds as a vehicle to help you, or you're just using the iron salts to accelerate an existing iron salt. These are applications of aerosols to sort of tip the chemistry that's already occurring naturally anyway in the atmosphere.
Okay, that sounds great. So it's just now that maybe that means you're widening the range of types of aerosol that you might be thinking of. Is that the implication or not? Go ahead and tell me more, David.
That's exactly right. I mean, I think the insight that Hans and Clive have developed is that we can take advantage of the behavior of the clouds. I mean, if you think about it, a lot of the reactions in the atmosphere are powered by the sun anyway, because it's available. And if that light's not heading down to the surface to be absorbed by the atmosphere below, then it can participate more aggressively in what's going on above the cloud.
Then tell me more what chemicals I don't need to know proprietary information, but last I heard it was iron salt, ferric oxide or something, and you were going to spray ferric oxide into the air, which was through a couple of other steps was going to knock out the methane and turn it into CO2 and water. Now, what other chemicals are you going to use, and how do they work now?
Yeah.
The new ones.
Shall I answer that?
Yeah.
Yeah. Yeah, it's ferric chloride. That's the old-fashioned name. Iron 3 chloride. It's iron chloride. Think of like sodium chloride. There's a salt.
Ferric chloride, not I said oxide or something. Ferric chloride. Very good.
That's it. Yeah. And so we still think it's a good idea, but we're interested in better ways or other ways or ways that could still include some iron 3 chloride, but nature's complex. Nature loves doing complex things, and so there are other things that could mean that we need to disperse a lot less iron 3 chloride and just a lot less stuff basically into the atmosphere. So one of them so Franz points this out, and I learn from Franz all the time that so there's another radical. So the thing is, the thing about methane is it plays hard to get. Methane molecules really kind of dodge the oxidation. They don't. We know that they burn for your gas cooker because it just keeps burning because it's hot. But on their own in the atmosphere, they just avoid oxidizing, being turned into carbon dioxide and water, which is what happens in the end. Something gets it in the end. It's an OH. It has to be an OH radical, something that's radical that hits the methane molecule. And this is why it lasts roughly sort of 10 years in the air, because if something gets it eventually. But before that time, it's, as you say, it's a very powerful warming gas compared to carbon dioxide. Now, chlorine radicals, chlorine also, it can operate as a radical. Single chlorine atom. Normally, chlorine goes around. Most things go around in pairs, oxygen and to get into the chemistry. But if you have a single chlorine atom, that also knocks out methane much more effectively, actually, than OH radicals, much more quickly. And so this is why we're interested in chlorine radicals. And chlorine radicals, they operate in clouds when you have a little bit of chlorine in the air. Now, of course, we know there's tons of chlorine in salt, sodium chloride. It's there in the sea, and you get sea spray, and then you get kind of all kinds of natural reactions that end up producing HCl. So it's hydrogen chloride. It's what's in our stomachs that makes our stomachs acidic, and it's in the air as a gas, very, very tiny concentrations, but even a tiny concentration of hydrogen chloride in the air gets utilized in clouds to make chlorine radicals, and that's what removes methane rather quickly from the air. And you get a much more hydrogen chloride at coastlines, for example, where there's a lot more sea spray because of the waves than you do far out at sea where there's nothing much happening. And so that's one of the things
that's different from what I'm used to hearing. So to say that again, if you do it close to land or on land, it's
right.
better.
So what we're saying is what we look at. What we don't want to do is do something that is unnatural. Okay, so we looked to parts of the earth which are something's happening very naturally, And at coastlines, that's where you find naturally the most hydrogen chloride in the air, apart from volcanoes where it goes through the roof, of course. But at coastlines, because there's sea spray, it produces, because sodium chloride, and it reacts with other components of natural components of the atmosphere, and it ends up producing hydrogen chloride gas. So it's hydrogen chloride, but very, very tiny quantities that have what's the word, disproportionate effect on removing methane in clouds. So this hydrogen chloride moves around in the air just like all other gases, and when it gets into clouds, we call it a catalyst because it speeds up the process of methane removal. Now, far out that, but of course, coastlines, that's not most of the area of the Earth. Most of the area is the big wide oceans. That's 70% of the surface of the Earth. And most of that area doesn't have much hydrogen chloride in the air at all, not much, because there is nothing like as much waves crashing around. So that's what we're interested in, is how could we first of all have more, as Cran said, condensation nuclei, so more tiny aerosol particles for water to condense on. That's what makes clouds brighter, and smaller droplets produce more oxidation, and then a tiny little bit more chlorine in form, starting with hydrogen chloride, just a tiny. I mean, these are, you could never smell it. It's a 1 part per billion is what we're talking about here. Increase it from parts per trillion to 1 part per billion, and this would have a marked effect, a large, very noticeable effect on the concentration of methane in the atmosphere. So I got all this from Franz, and so this is what we're working
now,
on.
what is this aerosol? What is the thing that you want to put out there? It's going to be the nucleus for these.
A new number of things. One thing we look at is shipping. Shipping produces all kinds of gases, and most of the time at the moment, one of the reasons we have this accelerated warming is because they've had to reduce the amount of sulfur. Now, that's for good reason. So what we're looking at is what can be done, what could be done alternatively with that sulfur and the other pollutants as well, which are also helpful. The nitrogen oxides are also very powerful at removing methane. What could be done with us? We don't have, and I don't think we have an answer that we could give you right now that would be suitable for this sort of presentation. But the other thing is, so that's one thing, but ships don't go everywhere. So we're also thinking about, well, could you have buoys spread around, perhaps self-positioning buoys that release, again, another kind of salt. It's actually, so one of the problems people have with the technology people have is making the particles small enough. It's very difficult to make nanoparticles. They're trying to sort of spray this seawater, but they're having trouble getting them small enough. But it's very easy to make very tiny particles simply by mixing gases that react together. And ammonia and hydrogen chloride react together to form another salt, which is ammonium chloride. And you can make ammonium chloride nanoparticles. So that's one of the things. And that's, by the way, that's a food additive. So that's not going to harm the ocean. And especially in the absolutely tiny, minuscule amounts.
Let me say something, Klaus.
Yep.
Many people know the German Nuremberg Lebkuchen. It comes into these Lebkuchen as medium to get them, like ammonium carbonate, to get it so it is totally unpoisonous.
It's called in English. It's called baker's ammonia. You just buy it.
Yes.
I never heard of it. Okay. I hear you trying to be super careful to make it clear that you're not going to do anything very poisonous.
Yeah.
I mean, the tone of voice indicates that you think there are things that we might be worried about, and you're going to allay our concerns. Well, I consider myself allayed because I'm looking for answers and I'll take almost anything you've got. So I'm an easy sell when it comes to this kind of thing. But I would like to know what it is that not that I understand, but is there any familiar product or chemical or something that you're going to spray into the atmosphere that I haven't heard of before that's going to have this effect of producing what, the ammonium
Chloride,
ammonium
ammonium
chloride?
chloride.
Okay.
Yeah. So it's
What
ammonia.
is the stuff? Okay, I use ammonia to clean my glassware and things like that, all kinds of stuff. And my neighbors, anybody comes in the house after I've used it, I think other people are more sensitive to it, but it's really something. I mean, you don't want to stand near that if you can't get other things to inhale.
Oh, but just like salt, so salt, sodium chloride, is a mixture of sodium, which is actually itself very dangerous, and chlorine, which by itself is very dangerous. But salt together is not dangerous at all. Okay. So ammonium mixed with chloride, the ammonium separately is somewhat dangerous, not as dangerous as sodium. And the chlorine, again, is the same thing. If you mix ammonium and chloride, you get basically something which, you don't want to be breathing it, but it's not very dangerous. So the wonderful thing about chemistry, the most wonderful thing about chemistry is that very small changes make a huge difference. And so ammonium chloride is much safer than ammonia, just like sodium chloride, salt, is much safer than sodium or chlorine.
Okay, now have I run into ammonium chloride in my travels around my kitchen?
Well, the products that create ammonium chloride, you may have, because it's actually relatively common. But the more common thing, which, as Franz was saying, is this thing called Baker's ammonia, which is actually ammonium carbonate or sometimes bicarbonate. And if you were to take that and put it near a very small amount of hydrochloric acid, now hydrochloric acid sounds dangerous, but it's actually all over the place. As Franz said, it's in your stomach. It's in your batteries, in your car. There's hydrochloric acid everywhere. If you were to put the simple Baker's ammonia and hydrochloric acid near each other, you get this white, you can do this yourself. You get this white mist. And that white mist, it's a chemical reaction of the gases. It's just the little diffusion. By the way, the other, the ammonia smelling salts that they use to like wake people up and things.
Yeah, I've heard of it. I've never seen it, but okay.
Yeah, it's basically, they're just very small amounts of ammonia. If you take these chemicals, which are very common, in fact, the drain cleaner is hydrochloric acid also. Now, you don't want to be drinking the hydrochloric acid. But in any case, if you put them next to each other, because it's way too concentrated, but even very unconcentrated, if you put them next to each other, the vapors from those combine to give you a very fine white mist. And that white mist is a relatively safe, again, you don't want to be breathing it, but it's fairly safe. You also don't want to be breathing salt vapor, right? So don't breathe anything. But even safe stuff, just because the lungs are pretty sensitive.
Yeah.
That vapor are nanoparticles of ammonium chloride. It's the combination of the chloride from the hydrochloric acid and the ammonium from the Baker's ammonia. Okay. And that mist is what Franz and Clive have hypothesized, and we're testing in the laboratory, will nucleate the water in the air to make very, very bright clouds, and also at the same time provide chlorine atoms that bounce around and grab the methane. Is that a little bit clear?
Yes. I'm not quite there, but I got
Was
a
that fairly
general feeling
accurate,
for it.
Franz and Clive?
Yeah, that's good.
Yes, wonderful.
Mhm.
And I think we must only combine this cloud whitening and methane depletion. That's a wonderful thing.
So we're
I've got a
testing this
question.
in the
Now there's chlorine over the ocean in the air because the salt water has chlorine in it. are you going to use anything from that chlorine, or are you going to have to bring, I'm now having an impression you're going to bring these two chemicals that you just talked about, Baker's and something else, and you're going to mix them up there in the airplane and dump it out. That must not be right.
Well, you could use the chlorine from the, so most of the chlorine that comes off the ocean is molecular chlorine, it's basically sodium chloride. And some of that does break down, the sunlight breaks some of that down, but not very much of it.
It is the phytoplankton, which makes a dimethyl sulfide, which oxidizes and therefore H2SO4. And this H2SO4 reacts with sea salt haze and produces HCl and sodium sulfate. That's a react. Only for explanation.
Yeah.
Okay, so let me, I mean, I don't want to go off. No, let's stay with this because I want to know how come we've got two different outfits here that are all doing research. And I gather you've talked to each other because you seem to understand, or you're talking the same language. So I'm interested in how you're cooperating. But first, just let me make sure I understand a little bit more about a tiny bit more about what you're planning to do. What would you do? Okay, now we've got, somebody would say now we made a big mistake by getting the ship tracks out of the equation, or the sulfur out of the these trails that ships make, because that's increased global temperature by something like 1 degree.
And
Maybe
methane. And methane jumped also for that.
methane jumped as a result of that.
Yes, yes.
Is that part of how you discovered this, that it has such an impact?
Yes, it's a little part of that. Yeah.
Mm-hmm, mm-hmm.
And it adds weight, basically. We see it in papers and we say, yeah, we're on the right track here. Because look, especially during the COVID period, the methane, the rate of increase of, I mean, methane is increasing all the time in the atmosphere.
But
this is not a good thing, just like carbon dioxide.
And it jumped.
But the rate of increase jumped but fourfold during the COVID lockdown period. That's what's most remarkable to us.
And they now believe, they being, I mean, I don't know who, believe that it was the same reason as that the ship tracks, when they banned the use of, I don't know, bunker fuel or some kind of fuel for
High
ships.
sulfur bunker fuel.
Okay, they stopped using that and therefore cleaned up our pollution, but made things worse in terms of global warming. And
So
after the fact,
can I?
people, yeah, go ahead. Sure.
Okay, sorry, because you brought up a couple of issues. So you used the present tense. You're like, you guys are spraying this into the air, and that's a turn of phrase. That's just fine, but this is still in the research phase.
Oh yeah. Okay. Well,
so I just want to be clear.
Should say you're thinking about doing this, and that's great. Let's talk about it. Good.
That's right. Right. We had, Rocio has secured some authorization to do some iron salt experiments off the coast of California, but we have this other approach is premature to get any kind of okay to even know if we can do it and experimentally validate that it might work.
Yeah.
So in the lab, right? So this is still, you're kind of looking right at the horizon here in terms of solutions. There's another thing I want to point out, which is there was a reason why the IMO, the International Maritime Organization, part of the UN, wanted the ships to stop using this high sulfur fuels, or to remove the sulfur emissions from burning those fuels, just as they did for the coal plants in the 1990s. And the reason is it's a pollutant, right? That's what caused acid rain. And so, sort of saying, well, you became extremely ill, but you lost all this weight. You look fabulous. I mean, I think it's, you want to actually think through the entire situation before, you get these panicky articles in the newspaper saying, "Oh my God, we made things worse," rather than making them better, right? So
Well, I don't have a position on whether I've heard that there are people saying, let's bring back the old dirty bunker fuel because it's better than, yeah. Okay, I don't have a position on that, but I'm open to all kinds of arguments. But mostly, I just want to know more about what this stuff is that you want to dump. I presume you'll be flying around in planes, or maybe you'll just do it from ships, and you'll emit this stuff. And what exactly are you going to spray around there? What is the stuff you're going to spray?
Well, we kind of said that and it got a little bit technical, so I don't know. I mean, it's either we're both exploring iron salt aerosols, and Peter is specifically focused on that. We have done a lot of work down that path, but are also exploring this ammonium chloride approach.
So it's ammonium chloride that you would be spraying. One thing, not
It's
you don't really spray it because
you don't spray it. It diffuses. All these things are like this. It basically, especially the ammonium chloride, it diffuses out into the atmosphere. What you do is you run vapor from hydrochloric acid, very, very not dense vapor, over solid, essentially ammonium carbonate, and this white nucleation. And by the way, the reason they're white isn't because they're already nucleating water vapor. It's the reason you can see them, I think. So anyway, the white stuff just diffuses out, and then you can use some kind of device to make it. We've designed various ways to solve the problem, and Peter can talk more about this of putting it out in the way you want it.
Now you're gonna you put a layer of something, and then you
a layer of very safe ammonium bicarbonate carbonate.
This is like the stuff I brush my teeth with.
Sure.
Okay.
It's close enough to the stuff you brush your teeth with. It's actually you cook with it, not brush your teeth with. I mean, I think what you're thinking of is baking soda, probably.
Yeah.
But in any case,
that's not what you're going to do.
Close enough.
Okay. All right.
It's the moral equivalent of baking soda. But if you put hydrochloric acid vapor over it, then it creates these nucleation. It creates this white dust that just it sits in the air. It's so light that it's actually just moves around in the turbulence of the air, and it will float up into the atmosphere, and it will nucleate clouds. You'll end up with a contrail behind a ship. I mean, ships already have a bit of a contrail from their stack, but this will be hopefully a big contrail following behind the ship.
Where would you lay this stuff down? Because you can't lay it on top of the water.
Oh no, sorry, it's in a shipping container on the ship.
On the ship.
At the stern of the ship, ship's going this way, this way.
And then you put this stuff on the deck, and
I think Peter, just it's just like blowing stuff out. It's sort of like a machine. It's sort of like your car that blows stuff out the tailpipe.
Yeah.
Peter's been working on some other methods for this, airplanes and various things. So maybe he hasn't said much. Maybe he can talk about different methods.
Well, are we ready to talk about the dispersal method? Okay. Peter, maybe that's what you want to tell me about.
Yeah, well, if I can back up, a quick summary. The last year has had a lot of progress in the field of methane oxidation. There are a number of papers published that you may have talked with Martin von Herpen and a few others who have published papers showing that the iron salt aerosol does operate in nature. And so it's good to know that it does work and that it's already a natural phenomenon, which allays a lot of people's fears. And there's been lab work done in Denmark, which I don't know the details, but showing that the iron chloride does work. So standing on that, then you're and so then Franz and the rest of the team here has been working on how to expand the iron chloride. So for example, the ammonium chloride is a very interesting addition. So I approach things from a sort of a simple perspective. So I ask, what's the minimum viable product? When these days, when you start a business, you usually want to start with just the minimum thing you can do, get all the processes going, and then enhance. And I consider the iron chloride to be the minimum viable product. It's been tested and quite well understood. And my favorite way of dealing with it is emitting it from either the land or probably ships, just because it's much easier to get permission to do things from ships than it is to do anything on land. And have iron chloride emitters on stationary ships off of the west coast of the Americas and Africa. And those happen to be the places we have the very minimum rainfall, because the efficiency of these things is controlled by how often it rains. When the rain falls, it washes the aerosols out of the air. And so the less it rains, the longer the aerosols stay and the more efficient. A ton of iron chloride or presumably ammonium chloride will stay up pretty much until the first rain.
Not to mention it's sunnier.
Yes.
Okay.
Yeah. And so that's the work I've done. I have a little article showing how we might roll out iron chloride globally in such a way that if the methane burst that's starting now, if that methane burst gets as bad as it was 50 million years ago, then we could expand the methane oxidation and prevent an extinction event. Because if a methane burst happens, it'll heat the planet so quickly that a lot of ecosystem will collapse.
Yes, I mean, that's one of the things that I have nightmares about. Okay, so I take it that what you're saying is that you aren't as confident about the prospect of this ammonia and hydrochloric acid as you are the iron's approach.
I had not looked into the ammonium, and I'm trusting everyone else on the screen to do that. I'm in favor of it, but I just don't know anything about it. I'm focusing on once we get something working with the iron chloride, then enhancing it becomes easy. The main barrier, and I think Ricio and David will agree, that the main barrier to doing this is the social acceptance of just actually restoring the climate.
Well, yeah, and social acceptance isn't totally irrational, although I think now often I think most people are crazy, but they're not. I mean, there are reasons to be apprehensive about potential negative side effects. Now, I've heard that one of the possible effects of marine cloud brightening might be excessive rain in places that you don't want it, Pakistan or who knows where. But so you'd have to look at, would that actually cause floods, for example? And the same way with something like this, what are the potential negative side effects that you would have to explore before authorizing this at scale?
Well, to back up a little bit. So the social acceptance or social license, it seems to be the main barrier, not the technical. And you're asking, well, there's probably reason that people are skeptical about these things. Well, what about if excessive rain happens? Well, excessive rain happens all the time. I mean, you read the news and you read about flooding all the time. So then the question is, if significant excessive rain happened associated with marine cloud brightening, what would we do? Well, we'd stop it. It would cost nothing, and in a week it would be gone.
Yeah, but
And
you'd want to start it up again because you got good reason to want to do it. You'd be very disappointed if you had to stop it permanently, right?
I think
Right.
Peter's point is it's easily controllable, which
Mm-hmm.
many other geoengineering projects are not.
Mm-hmm.
And so
Well,
having an easily controllable system is you can turn it on, you can turn it off, you can move it to different places. And that's much better than, for example, moving the Earth in its orbit or something, right?
Yeah.
So something that you basically can't undo.
Or
Right.
SAI, which takes so long that you might take a couple of years before you'd be over it. Okay. Well, what are the potential?
Here's my point. So my point is that the critical thing to do is to get a test happening.
Mhm.
And because most of the field says it's either impossible or unethical. Well,
Mhm.
once it's happening, it's proven to be impossible, so that one's out. And then if it happens and no one complains, then that throws out the unethical. And now we can get down to work. And so I'm interested in the iron, personally in the iron chloride, just because it's something that already exists and we can push that into implementation. Small scale, but just and in distant places where there's no lawyers to make $1 million from suing us.
Mhm.
But whether it has any consequence or not, I expect it will, but the main purpose is to prove it can be done and break through the main barrier of the social
But
acceptance.
your expectation is that, like the iron salt aerosol, you could stop it right
Yes.
away, and the effects. That's true for the iron salt aerosol as well as the marine cloud brightening, right? You stop it, and within days or a week, the
Yeah,
effects are gone, right? Well,
exactly.
the same would happen with this hydrochloric acid business.
That's
Yes.
right.
Yes.
Uh-huh. Okay, how much of the stuff would you have to do? I mean, is
Lot.
it in terms of feasibility, the amount that you would need to spray? How does that compare with some of these other things? Salt for marine cloud brightening, and
A way to think of it,
yeah.
Peter might have a different calculation. The way I think of it is you would have to put 1/10, roughly, hopefully better than that, that is 1/20th, but let's use 1/10 because 10's around. 1/10 of the amount of, say, ferric chloride or ammonium chloride that as the methane produced annually, which is 150 gigatons, is that right? Of methane.
Methane, 600 million tons, I think, a year.
Okay, 600
That's
million.
right.
So you'd have to put 60 million tons of whatever it is you're doing out there, right? Hopefully less than that, but that's a nice
Should be
round.
less. Quite a lot
Yeah.
less. Yeah.
But that's at full
Knock wood.
scale. And I think
That's at full scale. That's at full scale, right?
Yeah, I can't visualize how much that
No.
would
Well,
be.
no, but that's not that
Translate-
large. It's not that large a number. If you think about, if you look at once you get to the climate, like remember, we're putting out 600 million tons. There's just industry and cars and stuff like that. So that's 10
We're
times.
putting out that
Uh,
much HCl.
No, methane.
that's-
Yeah, and it's not just us, of course, it's wetlands and all the rest of it as well.
Oh, hold on now.
That's going to go up.
Well, hold on. Let me get clear. We have to do 1/10 as much of the methane as we're putting out, or we have to do a 1/10
Yeah.
of the amount that's being
Yeah.
of other stuff that's being emitted.
No, 1/10 of the amount of methane.
Well,
probably less. Call it a 20th, but 10ths are easy to work with.
Okay, but that's quite a bit. That's quite a
I'd
bit.
say less than that, Jeff. I'd put it
Me
put it
too.
less than that.
You knock wood, it's less than that, but we don't have
Yeah.
any number that even prove that a 10th is going to work. So 10s are
Well,
most.
okay,
Yeah.
let's say 1/10. What if you had to mobilize all of the ships
Remember,
and
right.
airplanes that you can get a hand on,
Oh,
how many airplanes and ships would you need?
I would-
Enough to fight a war or
no,
something like
well,
that?
yeah, no, the number, so you would be shocked at the amount of cargo a cargo ship carries, right? Cargo ships carry, is it hundreds of thousands of tons?
Yes,
Um,
hundreds of containers, hundreds,
thousands of
multiple hundreds
containers.
of containers, each of which can, be up to 20 tons.
Right.
Right.
So,
I mean,
so a single cargo ship carries, I'd say probably, I have to run this number, I haven't done it yet, but probably like over a year, I'm talking about, probably 1/100th of the amount that we need to do this. So that's only 100 cargo ships for a year, right? Quote me on that one. I know this is going out live on YouTube. That number I haven't done, but it's the sort of order of magnitude we're talking about.
All right.
So when you think of it from the side, I mean, the size of scaled industry in the cargo industry is unbelievable. So these huge numbers don't seem so huge when you think about the scale of the cargo industry.
All right. It'd be a big operation. Now, would it be a bigger
Big operation,
than
yes.
the iron salt aerosol operation?
What's around the same? It just depends what you're putting
yeah.
out.
And
All
we
these
can,
catalysts are, all these catalysts.
A proviso I want to put in is, and especially for you, Jeff, that when we're looking into the future, given that the main barrier is just getting the first thing to happen, that I always recommend that we do our estimates based on just a simple best estimate, not the conservative estimate, but like Clive said, there's reason to think that we could do it with Franz's paper, the 2017 paper said something like 250,000 tons of iron chloride. And so if we just say, okay, good, that's published and peer reviewed, and if we run with that, then that comes out to blah.
Right.
And now that becomes our baseline. And
Right.
that way we can get started. And if it's 1,000 times more, well, we've all been in 100 times more. We've all been in projects that required 100 times more. It's
Fine,
like,
a 250,000 ton. 250,000 tons sounds big, but it's not.
Right.
Right.
Anyway, Meta, does that help?
Oh yeah, I mean, I'm not good at that kind of thing at all, but at any rate, I feel confident that you guys are good at it, and so I trust you.
Yeah.
But now let me think. Some of this stuff won't it'll get there and it won't combine, or now with iron salt aerosol, some of the iron would fall out of the sky not having hit a methane thing. Therefore, you have to think about what is the effect of the iron in the ocean where it falls or wherever it falls. And now, I'm trying to imagine if you pour this stuff or spray this HCl onto whatever this white stuff is, I've forgotten, and the only thing that comes off the ship, let's say you're doing on an aircraft carrier where you got a lot of surface, and you put a layer of this stuff and you spray it, and what comes up is vapor that results from the only vapor coming up would be whatever it resulted from the interaction between these two chemicals. So there wouldn't be anything extra left over to contaminate the world or the ocean.
you can't.
Yeah, there's no contamination. I mean, there's contamination, but the ocean has so much chlorine, ammonia, and iron. I mean, it's like full of chemicals that it would have. I mean, it will very slightly impact the surface, chemistry of the ocean in those little regions where it's done.
Well, that's the kind of question you're going to have people asking you. What are you going to do putting hydrochloric acid into the ocean and killing all the fish or whatever they're going to say?
There's research going on in this.
Huh?
Well, there's research going on in this. There are many people. We have a colleague at Irvine who's studies this kind of thing, who we're working with to estimate the effect, biodiversity impact in the ocean.
Okay.
For instance, you use only 0.2 micrograms per cubic meter of ammonium chloride to whiten a cloud. That's a very, very tiny amount. And if this falls with some rain weeks later into the ocean, it will give a little bit of food for the phytoplankton. It's the same like iron. If it falls into the ocean, it helps the phytoplankton
It does?
to bloom.
Which very slightly, and the phytoplankton, the Prochlorococcus and the cyanobacteria, which are the base of the food chain, actually, if they're upregulated a little bit, that draws down carbon dioxide.
So
But
the
it'll
last
have a
part of
very
your
small.
sentence. Repeat the last sentence. If it's up a little bit, then what happens?
So there have been many experiments done over the past decade. Peter knows more about this. Well, Peter certainly knows a lot about this. I don't know. I've measured his differential knowledge from me, but anyway, that basically those are nutrients, the ammonia and the well, they all are, but the ammonia and the iron. There's no lack of chlorine in the ocean. Those are nutrients that phytoplankton. So phytoplankton are the base of the marine food chain. In fact, they're the base of the entire Earth's food chain.
Mhm.
And they also draw down, they create half the oxygen roughly and pull down half the carbon dioxide. And so if you were to upregulate them, that is to say, give them a little more nutrient, many people, and by the way, we're talking about very small amounts of nutrient, but if you were to give them more nutrient, it's probably a good thing, not a bad thing, because basically what you do is you draw down more carbon dioxide and you increase the food chain.
And because the ocean is stratified by the heat, the upper ocean layer is too warm, much warmer than the ocean layers below. And this makes a stratification, and it blocks the nutrient exchange between the lower layer to the upper layer. So a phytoplankton suffers from this climate change also. And if we give it a little bit of a nutrient, it's only tiniest amounts.
In comparison with,
would
for
help
example,
the
the people who want to do this ocean iron fertilization, they would be affecting the chemistry of the ocean substantially more than what you plan to do. Is that right?
Yes.
Yeah. I've done the calculation.
Here's a way to do the comparison that's easy to understand, perhaps. Okay. I mean, Jeff's talking about tens of millions of tons, right? He said 60 million tons, okay, of iron chloride, only part of which is the iron. The wind that picks up the Sahara blows across the Atlantic and deposits iron to fertilize the Amazon. In the process, each year, it drops about a gigaton of iron into the Atlantic Ocean. Okay. Okay, a gigaton, 1,000 megatons. So if you think about using 60 megatons of something spread around the Earth, the amount that you're doing over the Atlantic is negligible compared to what nature is already doing.
And that was
so the actual numbers, we'll figure out where they are, but they're probably less than 60 megatons. But the point is, we're talking about nature's doing this and you're doing a little bit more. Okay, now we all know from driving our car, every car doesn't make a big difference, right? But the sum of the cars adds to a lot. But this is one project you're talking about, one activity. So just sort of back of the envelope says that it's a negligible amount. And still have to do studies. You still have to have it's really true, but it just your sort of the rule of thumb says we're in this particular issue is in a safe region.
Okay. And the key thing, Meta, is that it's putting the iron at the right place in the right time. Because you would say, well, if the nature's doing a gigaton, how can our doing 60 megatons, doing a whatever that is, a 50th, 20th of it, make any difference? And the answer is we know we can figure out exactly the optimal place and time and concentration.
Mhm.
And that's what we're doing. That's what makes me very excited about what Franz and Jeff are working on. Is my job is to make sure that the orchestra plays, that we can actually do the testing. Then their job is to tune up the violins and the oboes so that they actually play well. So
Okay.
they're complementary.
Yeah. Well, our time is up, but I don't want to leave without giving Rocio and Adele each a chance to say a little bit. So, because neither of them have spoken at all, Rocio, what would you like to add to this conversation?
But I am following the act, and my job is to bring in communities into this work, because this is all scientific and all this stuff. But you know, so I'm always listening for who's affected, who needs to know, who do we need to engage. So the whole aspect of this, and making sure that we have proper regulations, that we have permits to do what we're doing, and that is safe for people, because my job is to communicate this to just regular folks.
Good.
And of course, the environmental justice part of it, and all these boxes.
And I'm glad they thought about that. It is very nice. We've also lately been talking about the importance of having all the stakeholders consulted along the way. I think one of the things that annoyed the people in the Alameda area is that they weren't invited to participate in making decisions about whether or not to spray that stuff from a ship in Alameda. So, and I think that's also the effect that kind of blocked something that David Keith was trying to do in Scandinavia. He hadn't asked the Sami. And so it's a good idea to ask people, but I can't think of whom you should ask about spraying on the ocean. Well, I'll leave that up to you, Rosia. Okay, thank you. Anna, oh, yes, anything? Okay.
No, it's challenging, yes, and it's moving. Thank you.
Adele, thank you for coming. You came in late, so I don't know whether you got the whole picture, but do you have any comments? Don't destroy the whole edifice, please, because we don't have time to put it back together.
I apologize for coming late. However, in a part of my professional background, not a significant chunk in fairly recent times, is something called environmental technology verification, which is run by governments in the U.S. and Canada for sure, and Europe as well, in various ways. What I want to know, and I think Peter's heard this before maybe, is give me a very rough time scale of when someone will run an experiment that will get verifiable data, because I believe that would open the door to all sorts of funding and moving forward.
How big an experiment?
Well, anything that you can verify that yes.
Oh, we've already got verifiable. We already have verifiable data in the lab.
Okay, well, no, I want verifiable.
That's what I was asking. Okay.
On the ocean.
Well, we have verifiable data in the open, but not in the ocean. That is to say, the open sky.
Well, anyway, so when could you go to the ocean?
Well, I'll give an approach, which is it all depends on funding. And we're making very good progress on our ocean fertilization work. If it continues going ahead of schedule, then we should get some ocean fertilization testing done around the end of the year, beginning of next year. That is likely to open the door to funding for the methane oxidation, because what I see is no one wants to touch it, because no one wants to touch the high voltage lead that is environmental testing. But if once we demonstrate that it can be done, then I think the funding will come quickly.
You were wonderful. This is really I'm delighted that you're actually making some progress with doing it.
Mm.
Because I thought, most people are worried about how constantly being blocked, but it sounds like you have things about to happen. So our time is well past, but it's been extremely interesting. God bless you. I hope it works. Keep me posted, because I'm ashamed to say I had no idea about what you were doing until this very hour. So thank you very much. And I'm probably going to get back to all of you again for another stint here. Okay.
Great.
Thank you,
Bye-bye.
Meta.
Yeah.
Bye-bye.
Thanks, Meta.
Thank